So good morning, everyone. Now we look at the gaseous dielectric materials. And although this document will look a little bit different from what you have, I've just added one page. And this is just to illustrate what it is we are talking about, the gaseous materials or the dielectric materials, so to speak. Most of the applications for dielectric materials is as insulators, to insulate electrical conductors, and also in the manufacture of capacitors and such like things. So what happens is that we consider a parallel plate capacitor. Yeah, that should be parallel plate capacitor with a potential difference V impressed across it as shown. What we'll realize is that positive charge and negative charge will be deposited on the two plates, and the force of attraction between the coulombic force of attraction between the charges on the plates will cause a force F to be exerted onto the dielectric itself. And this force F is from Coulomb's law proportional to the distance between the charge separation square. Yeah. If the tensile strength of the dielectric is low, then the force will become larger as the dielectric gets squeezed between the plates. The distance L between the plates will decrease and F will increase, and in the end we may have a rupture of the dielectric or a short circuiting of the two plates, okay, if the dielectric is squeezed between those two plates. Hence, insulating materials must have the following general characteristics. One, they must have high, ideally infinite electrical resistivity. That is, for them to be lossless, the sigma or the conductivity must be 0, so that they can provide isolation between conductors. They must have high mechanical strength to provide mechanical support, and high thermal conductivity to aid heat transfer, because most of the times we may have dielectrics that are a bit lossy, and that losses, okay, the losses will always be in terms of heat, and the conductivity must be removed, or the heat must be removed from the dielectric, because as the heat increases or the temperature of the dielectric increases, what would happen is that the dielectric mechanical strength will decrease, and therefore we have that problem again of having the dielectric being squeezed further. So several insulating materials are often used together to provide a complete insulation solution to any given electrical problem. So the insulating materials may be in the gaseous phase, or the liquid phase, such as oils. This would be things like sulfur hexafluoride, and that could be oil, mineral oil. Or in the solid phase, such as mica in small capacitors used in electronic devices, or even wood in some places. So the desirable electrical properties that insulating materials should have may include low loss or dissipation factor. That is, we have to remove as much as possible the free carriers, charge carriers in the material. 2, high dielectric or insulation strength, and so forth. Dielectric or insulation strength is the highest electric field that can be applied across the dielectric before we start having impact ionization of the dielectric, leading to failure as the charge carrier density increases. So all electrical circuits will employ insulating materials, e.g., in housing wiring, we have wires that must have the insulation. You don't want to be touching on the electrical wires and getting electrocuted. So general insulation for conductors, the printed circuit board itself is always placed on a dielectric substrate, which for the ones I'm sure you guys have come across would be those like the fiber or the epoxy glass fiber printed circuit board that you use in the laboratory or in printing your circuits in your project. So the choice of a dielectric for a given application will often consider material properties such as 1, the mechanical properties such as tensile or impact strength. That is, impact when it's hit, does it rupture or does it stay intact? Tensile is when you are exerting tensile forces on it, especially for insulators used, say for example, to insulate transmission power transmission lines. The tensile or compressive moduli, such as Young's modulus and the bulk modulus. And 2, it could be thermal, that is, what is the maximum or minimum operating temperature range for a given dielectric lifetime. Sufficiently high thermal conductivity for good heat transfer, and the important considerations that we are continuing now would be the environmental. Say, how does it resist to atmospheric oxidation? We know some dielectric materials which are very, very good as insulators, but they are also detrimental to the environment because they are poisonous, such as that's called ascaride, I think ascaride oils from some kind of plants. So susceptibility to light and other environmental high frequency radiation, that is, does the light or the radiation cause failure of that dielectric? And 2, how rugged it is in the environments that include acid, alkaline fumes, or high humidity, such as in industry where we may be producing acids or we may be producing chemicals. We still have an electrical supply in these areas. They could be also electrical, where we have the electric strength is the most important, the dielectric constant and the loss tangent, because say for example in an electronic circuit, especially in the area of miniaturization, the wavelength or the speed of or the velocity of the wave propagating in these materials will decrease with the increasing dielectric constant, because we have seen that the velocity of light or the phase velocity of light is proportional to 1 over, okay, it's proportional to 1 of root epsilon. That is the dielectric, electric permittivity of the dielectric. So it could also be economic, okay, which is an important consideration when we are looking at projects that will require bulk materials, okay, and cost is often a significant consideration. So the electric properties of materials imply the, in the response of the material to electric stress at the electronic level, where we saw the polarization, the electronic polarization will bring in issues of the, we saw the polarizability is a frequency dependent property of the material. To the atomic level, and then molecular level, and finally, we say that the study of the dielectric properties of a material is therefore usually a study of the material's electric permittivity relative to that of a vacuum. And this study of the electric relative permittivity is applied in many areas, such as, say, for example, you could be looking at, say, you are studying moisture, okay, in drying maize and the likes to reduce aflatoxin and the likes. You can always, the epsilon R will depend also on the moisture content of the material you are trying to study, and therefore you can study its whatever to get the humidity or the moisture level in grains and so forth. You could also use it because epsilon R, the square root, is the reflective index. You can use it in a reflective kind of way where you are trying to see the reflection of radiation, and this is used especially in measurement of the testing on blood, the human blood, and in medicine and so forth. So there are so many applications for which the study of the material, the electric constant, is usually of use. So important questions that are investigated in this study will include the relationship between the measurable or macroscopic electrical efficient and the microscopic quantities. And two, the physical origin of epsilon R in the different materials, and temperature and frequency dependence of epsilon R. So important considerations are such phenomena such as polarization of the dielectric loss studied as a function of frequency and of temperature. The important results from a study of electric fields will be quickly browsed through in the following slides, just to refresh. And these are the Coulomb's law, which states that when two positive charges Q1 and Q2 are brought together, okay, a force F is established between the charges, which is inversely proportional to the square, the intervening distance between the charges. And it will always be in a direction that is pointing directly away from one of the charges. So if R cap is the unit direction vector that is defined from one of the charges, then F will be given by R cap Q1, Q2 over 4 pi epsilon R squared, and where epsilon is the electric permittivity of the medium surrounding these charges. Now, if Q1 and Q2 are of opposite side, you already see that R cap is going to be negative. So in SI system, that is the standard system of units that we use, F will be given in newtons, and epsilon will be in farads per meter, or F per meter, when Q is measured in coulombs. So any charge delta Q in the vicinity of a system of charges Q will experience a force delta F. And the region over which the system of the charges exerts its influence is known as the electric field. So the strength of intensity of the electric field at a given point is defined in terms of the force per unit charge on a positive test charge placed at that point. So, and therefore we can define E that we've been dealing with as the limit as delta Q goes to 0 of delta F over delta Q equal to dq of F. Remember, although we are using the usual symbols for derivatives, this derivative is not a true derivative because we know that delta Q cannot actually go to 0 because the smallest charge that we know is the electronic charge, which is 1.6 times 10 raised to the minus 19 coulombs. Okay, it can never go to 0. And therefore, this differential is a fictitious differential. We can call it not a proper differential, so to speak. So for a point charge Q in a medium of permittivity epsilon, then E is given by force per unit charge, and we just divide by one of the charges, and we get Q over 4 pi epsilon R squared. G as R cap given by Q over 4 pi R squared, which is the surface area of a sphere. And the class is getting smaller as we go towards the Christmas break. I don't know what's wrong with you guys. You don't like class or what? So I'm going to take a small break. Okay, let's meet after, on the hour. Okay. Yes, thank you. So electric breakdown. And one of the major issues that bring this about are usually radiation from the environment and the ionization. It's the ionization it causes on the gas molecules. So we say that air is an excellent insulator at normal temperature and pressure. And under the conditions, air will support conduction current densities on the order of 0.1 nanoamp per centimeter square. So the origin rays, which are energetic particles coming from origin, there will be yes. Yeah. Who wants to be excused? Hello?
Excuse me?
Yeah.
At around 9:20, you left the meeting and there were no slides, so we were waiting for you to come back. You came back like 5 minutes ago.
Oh. And why didn't you tell me? And I just kept on talking. So what did you get? Hello? So does it mean I have to repeat? So just
the last thing you mentioned was the electric flux at the beginning when you're talking about the dielectric properties of materials.
And why? Okay, you should have given me some alert actually, so that I can know what are those things. Did you get the Coulomb's law?
Yes.
So some of the material, of course, you have already covered from the previous talk. Yeah. So we started with the Coulomb's law. Hey, help me here. Can you see this?
No.
Excuse me, people. Are we going to be cooperative? Yeah, you take field. So okay, then let me just try to follow this. So we talked about the important dielectric properties of the materials, and we say that the important questions that we are trying to follow or macroscopic dielectric coefficient and or microscopic quantities. We also talked about the physical origin. Does it mean I've lost again?
Excuse me, sir. We cannot see the slides you're presenting.
Okay. So You cannot see them. Okay, let me try to arrange that. I'm sure it must have lost it. Let's see the interest. Share that. Hide. Now, can you see it?
Yes, you can. Thank you.
Yes. So what I mean is that the general dielectric properties of materials will include, that is, we are going to investigate the relationship between measurable dielectric coefficient and macroscopic quantities, the physical origin of epsilon r in different materials, the temperature and frequency dependence of the dielectric constant epsilon r, and the important considerations will be those phenomena such as polarization and dielectric laws that are studied as functions of frequency and temperature. And the important results from electrostatics, okay, we just cover this quickly and look at what we call the Coulomb's law, where we say that when two positive charges Q1 and Q2 are brought close together, okay, to a distance r, we see that the force F is established between the two charges, which will be inversely proportional to the square of the intervening distance between the charges and in the direction pointing directly away from one of the charges. And if you take r cap as the unit direction vector defined from one of the charges, then you can write that F is going to be given by r cap multiplied by the product of the charges and divided by the surface area of a spherical, the spherical surface area, okay, where we are assuming that the charges Q1 and Q2, influence of Q1, if Q2 is the test charge, and then Q1 will be a point charge, and will influence its influence will be symmetrical about that charge. Okay, epsilon is usually referred to as the electric permittivity of the medium that surrounds the charges. And we say that if Q1 and Q2 are opposite charges, or opposite sign, then the r cap will be a negative vector. So in the SI unit system, we say that F will be in newtons, epsilon will be in farad per meter, okay, is defined as a force per unit charge. That is, if any charge delta Q is in the vicinity of a system of charges with a combined charge Q, will experience a force delta F, just like we have seen there. Now, instead of using by the region of our influence is then known as its electric field. And the strength or the intensity of the electric field at a given point is defined in terms of the force per unit charge on a positive test charge placed at that point. So hence, E, that is the electric field intensity, will be defined as the limit as delta Q, the test charge is made to go to 0, of those two dq and F of the force F. This, I said, is not a true differential because the charge delta Q, the smallest we know in the universe, is an electronic charge, will never go to 0. They are discrete value. So, but for all practical purposes, we can always assume that that one is also a continuous function, and therefore just use it as it is. So for a point charge Q in a medium of permittivity epsilon, it will establish an electric field defined as r cap Q over 4 pi epsilon r squared. And this we see is charge per unit, force per unit charge. So electric displacement. So a positive charge, electric charge, is regarded as establishing an electric flux that is stringing out the electric displacement of flux lines that will be crossing a unit surface area that is normal to the flux lines. And therefore, for a point charge, okay, will be spherical about the point charge, defined as r cap q over 4 pi and multiplied by r squared, where the 4 pi r squared is that surface area of the sphere with a radius r and centered at the point charge. And therefore, we can see immediately that the electric displacement is just simply the epsilon. But epsilon is a tensor, and D and E will generally not be parallel. So the material that is filling the region of interest with those which have deal with isotropic media in this course. Another important theorem is Gauss theorem, which allows us to compute charge or to measure charge in a given area. And this states that the total electric flux that is emanating from a volume V through the closed surface S that bounds V is equal to the total net charge that is enclosed within the volume. And therefore, if we have charges, discrete charges, the interior displacement will be equal to the sum of the charges enclosed. And therefore, the n cap is, of course, defined as a outward unit number on S. So D is then the flux crossing S. So when the charge distribution within the volume enclosed by the closed surface is continuous and of charge density rho, then we can say that the normal component, the integral of the normal component of the electric displacement is just equal to the volume integral of rho, that is the free charge. So what is the dielectric constant rate? If we consider a capacitor of capacitance C naught consisting of two conducting plates with a cross-section area A and suspended in free space at a separation D, then the plates will be connected to the terminals of an AC source, then with an open circuit voltage V equal to V naught exponent of J omega T, that is a phasor form, then the capacitor, the charge on the capacitor in the phasor form capacitance multiplied by the voltage across it. And the charging current will therefore be given as the time rate of change of that charge on the capacitor, and we see that is just going to be J omega C naught multiplied by V. And therefore, we see that the charge current IQ is going to be, will lead the voltage by pi, by 2 or 90 degrees. If we consider a case in which the space between the plates is filled with an electric material of an electric permittivity epsilon, the capacitance will increase to a value given by the ratio of the electric permittivity of the material to that of free space and multiplied by C naught. And therefore, so the charge on the capacitor will therefore be given by Q epsilon R multiplied by the free space capacitance multiplied by V, and the charging current therefore will be given by IQ multiplied by J omega epsilon R and C naught of V. So since no dielectric material will be perfect, is a perfect insulator, it will always have some as low concentration with the voltage, and they give it the symbol I of I, and it will be given by the conductance of the dielectric and multiplied by the voltage across it. Okay, so the total current therefore must be given by I equal to the in-phase current plus the quadrature phase current. and this will be given by the sum of the conductance of the dielectric and the capacitance, J omega, and multiplied by the V. So the current will therefore lead the voltage by an angle theta that is less than 90 degrees, that over pure capacitor, that is lossless capacitor. And theta will be given as the arctangent of the quadrature phase current component divided by the in-phase current component. So the parameter of importance in engineering is what we call the power factor, and it's usually defined as the cosine of theta, okay, and given as the in-phase current divided by the total current. And this is just given as the conductance over the total admittance. So the angle delta L between the total current and the quadrature phase current is usually referred to as the loss tangent, and it's related to theta as 90 minus theta, as shown in that diagram. So the phase angle, okay, the loss angle will then be specified in terms of its tangent and then referred to as a loss tangent. And from delta L is just 90 minus theta, so that the tangent of delta of theta, or the cotangent of theta. So if the loss current, okay, the in-phase current component is considered to be purely from a finite conductivity, then the capacitor could be modeled as a lossless capacitor, okay, in parallel with a conductance G. So the loss tangent is inversely proportional to the frequency and is observed in water at low frequency, forms per meter. So this simple behavior is not observed in most dielectric materials, and therefore it means that for these materials there are other sources of losses besides. So we may account for the dielectric loss by defining an equivalent permittivity epsilon equal to epsilon prime minus J epsilon double, defined with that must be negative because we are trying to represent count for the element by I equal to J omega epsilon R C dot V, and we can see that it will have an epsilon R prime into 1 minus that C naught and multiplied by V. And hence, we can see that the conductivity, the conductance of the material is just equivalent to omega epsilon epsilon R double prime multiplied by C naught, and the loss tangent just simply the ratio of the imaginary to the real part. Therefore, epsilon prime is generally called the real dielectric constant of the material, and will describe the dielectric properties of that material at any given frequency f, independent on the circuit in which it is being used. And therefore, epsilon double prime will always be specified. This epsilon prime will be specified by the manufacturer of the dielectric, and the loss tangent will be given to represent the epsilon double prime. So if we assume uniform dielectric field in the region between the capacitor plates, then we can write that the magnitude of the field is going to be given by V by D. The electric field on the bound charges in the dielectric will then describe the effect of introducing the dielectric between these plates. So E will displace the bound charges slightly relative to one another, and with positive charges being displaced in the direction of the field. So each molecule hence will acquire an electric dipole moment that is parallel and in the same direction as E. So the number of electric dipole moments per unit for the polarization vector, and P is in general proportional to E, except in the materials that we call ferromagnetic materials. And therefore, P is just going to be given by epsilon naught multiplied by the chi of E, which we call the electric susceptibility of the material, and multiplied by the applied electric field. So this chi E will depend on the local field or on the applied field in ferromagnetic materials. The electric polarization will are usually specified through the electric displacement D, as D equal to the free space displacement plus the polarization of the material. And in free space, we find any material to polarize, the P is going to go to 0, and therefore you can see that the displacement of free space is simply epsilon naught multiplied by the applied field. So in a dielectric, we add the chi E, and we see that that is going to be given by D applied to the electric field. And hence, you can see immediately that the electric constant. We look at the molecular properties of the dielectric materials, and we consider dielectric material with n molecular dipole moments per unit volume, each of average dipole moment P. The dielectric polarization given as n multiplied by that will be proportional to the local electric field intensity EI that is acting on the molecule. And from yesterday's lecture, we said that EI will be different from within the polarization of the dipole moment as a polarizability factor alpha multiplying the unit volume in the material, then be given by n, given by the Avogadro's number divided by the molecular weight and multiplied by the mass or the density. We note that yesterday we saw that there were 4 distinct mechanisms that will contribute to the molecular polarizability alpha, and this will include electronic polarizability alpha. E has ions, and the dipole orientation of the polarizability alpha D, as when we have the dipole trying to realign with the applied field, and also interfacial. This always occurs only in. So when an electric field of intensity is slightly with the heavier atomic nuclei, and therefore each molecule will acquire an induced dipole moment of average value PE and related to the electronic polarizability, which we give the symbol alpha E as PE equal to alpha E. Trying to form molecules, the charge distribution is usually asymmetric between the atoms forming that molecule, and the valence. So applied field that act on the atoms in the molecules and will distort the rest charge. Distribution of the charge dipole to the polarizability of the ionic polarizability and multiplied by the local electric field. So electronic and atomic polarizabilities are common to all molecular dielectrics that we shall meet. So in many materials, many have permanent electric dipole moments that arise from the asymmetric charge distribution. And such molecules will then be said to be polar or paraelectric. So the permanent dipoles in polar dielectrics, each of dipole moment P will tend to align with the applied field in the direction of the field. And the alignment will, however, be opposed by the random thermal motion of these molecules. We know that if the temperature is different of a material is different from the absolute zero temperature of the atoms about their equilibrium position, say in a solid, or a thermal movement of the molecules in a gas. And this will oppose the alignment of the dipoles with the diagram will be set up at a given the direction of each polarization of the material, which we are calling P. And can then be shown to be given by alpha D equal to the modulus of the dipole moment square divided by 3 times kT, where kT is the thermal temperature with K the Boltzmann's constant from the molecular theory or kinetic theory of gases. So alpha E, alpha I, alpha D are all due to displacement of charge that is bound to the atoms or molecules. However, if any charge migration may occur can occur in the material, and this will always happen in practical dielectrics, which have a finite amount of free charge, the migration will contribute to the conductivity of that material. And in some dielectrics, the migration of the charge will be trapped at the interfaces between the components of an homogeneous dielectric material, and therefore set up space charges. And these space charges will constitute a dipole, an electric dipole. So negative space charge will be toward the positive plate of a capacitor, and the positive space charge will be toward the negative plate, and then constitute an electric dipole within the dielectric, and therefore contribute to the total polarizability all over of the facial polarizability alpha electric materials. Okay. So the local electric field intensity is proportional to the applied electric field E, but it's increased by a factor due to the surrounding dielectric dipoles. And we remember from yesterday, we had what we call the G factor. So the local field EI is given approximately by the Mossotti relation, that is given by the real part of the dielectric constant plus 2 divided by 3, where we have assumed do not have permanent dielectric. Dipoles are widely separated, that is, they are far apart, such as would be in the case of a gas or a dilute solution. They are randomly arranged or in cubic symmetric crystals in solids. So the Mossotti relation regards an individual molecule as localized in a spherical cavity, and will neglect any interactions with the neighboring dipoles. But this, in practice, will always occur. So E, the applied field can be eliminated Clausius-Mossotti equation given as the molar polarizability Na multiplied by alpha divided by 3 epsilon naught, and this gives us a ratio of epsilon r prime minus 1 over H divided by the mass of the material. The Clausius-Mossotti equation therefore relates the molar polarizability of the material, okay, to the dielectric constant of the dynamics. Under unidirectional or DC or very low frequency, alpha will be the sum of the 4 different polarizabilities mechanisms. That is the space charge, the orientational, the ionic, and the electronic. So each polarization is characterized by that relaxation time, tau, which represents the time that it's taken for the polarization to respond to the applied field. So electronic polarization is rapid, usually about 0.1 femtosecond. Ions are heavier and therefore respond with a characteristic relaxation time Ti on the order of a picosecond to 0.1 of a picosecond. The orientation of polarization, the relaxation time, will depend on the nature and state of the material, as well as temperature and viscosity. Temperature randomizes the orientation or the alignment of the dipoles with the applied field. Viscosity opposes the alignment, because this viscosity is the friction. If you say, for example, a liquid or a gas, and will generally, therefore, TD will generally, therefore, lie between 100 picosecond to about a millisecond. So solid materials will exhibit a broad distribution of the dipole orientation and relaxation time because of the microscopic variations in the molecular environment. So interfacial polarization relaxation time will also depend on the conductivity distribution in homogeneous materials, and will generally be long, usually on the order of a millisecond to 1 second. So an alternating electric field of frequency f, each to the total polarization, as long as the period of oscillation characterization and the characteristic relaxation time tau of that mechanism. So polarization can then be able to follow to establish itself completely before the ratio, if ever in effect 1 over tau, ordered as the space charge relaxation time, the orientation of space relaxation time, the ionic, and then electronic. And hence, mechanisms becomes insignificant in the same order as the signal frequency is increased. This is important, especially when we are trying to measure capacitance of a system using alternating current. So in homogeneous material, the alpha SC does not vibration being trapped, and therefore will expect no dispersion when the material is non-polar as well, to frequencies far above or 0.1 terahertz towards the optical frequencies. So the dielectric coefficient will then remain constant. This diagram is what we have already seen from yesterday's lecture. It's a qualitative depiction of the frequency response of the real part and imaginary part of the dielectric constant. So, slides. Hey people, let's have some feedback. I'm repeating myself again, so please let me know whether you are able to follow me. What does silence mean? Well, I'll just continue then. So the atomic polarization decays in the electric constant at optical frequencies. This is the only polarization that can follow the field at that high frequency. So dispersion of a transparent material over the visible spectrum is usually called anomaly due to the resonance at the natural characteristic frequency of the electrons in their respective and atomic energy levels, which we found from physical electrons to be given as En equal to NHF, so to speak, where N is, of course, the resonances will occur, and these correspond, they combine to produce an overall optical dispersion. This is an important characteristic, especially for those of us who will be dealing with optical communication using fiber optics. So each electronic resonance has an associated optical absorption band that corresponds to a peak in the dielectric loss factor when passing through such an resonance. And energy is dispersed as heat in each dispersion region and associated with the relaxation of the other types of polarizations. So, and therefore, each spectral region over which epsilon r changes, the loss factor passes through a broad maximum that is centered at the frequency equal to the reciprocal of the relaxation time. So in radio frequency, in the relaxation of dipole orientation in polar dielectrics, the loss may be spread over the whole radio frequency region if there is a distribution of relaxation times, as many practical polar materials do have this kind of behavior. And this can thus be reduced to tolerable limits. So a relatively constant loss tangent coupled with a dielectric constant that decreases slowly with increasing frequency is symptomatic of such a behavior. So in non-polar materials, the electric loss is very small and can be attributed to traces of polar internalization or conductivity at audio and power frequencies. So interfacial polarization is associated with conductivity and rather than dispersion. And therefore, no change in epsilon r will occur as the frequency is varied. So increased temperature has the general effect of reducing the relaxation times. And hence, a shift in the dielectric dispersion and the absorption profile towards higher frequencies. And this may have important practical effects, such as, say, for example, petroleum oil used in transformers will exhibit low dielectric loss at 50 Hertz at room temperature due to conductivity, and a significant increase in the loss tangent as the temperature is raised to between 60 and 70 degrees C. And hence, when you are choosing a dielectric material, its dielectric behavior over the full working range of frequency and temperature will be an important consideration. For ferroelectric materials such as barium titanate, okay, spontaneous electric polarization is exhibited in some regions of the dielectric, which are called domains. And you can remember the domains from the physics when you covered magnetic materials, and we say the magnetic materials are usually have domains, so to speak, with domain walls and the like. and this will be over a certain temperature ranges. So the application of electric fields to these materials will therefore cause the alignment of domains in the direction of the applied field and will result in high electric depolarization and an associated large real part of the dielectric constant, usually to the order of 1,000. So epsilon r in this material will have a magnitude that is dependent on the intensity of the applied field. That is, the materials are nonlinear. The history of the material has a history of applied voltage to it. And therefore associated material memory, gaseous, insular, argon, hydrogen, and so forth. Oxide gases such as carbon dioxide, sulfur dioxide, and etc. Fluoride, with sulfur hexafluoride being the most important insulating material in high voltage application. Freon gases, we know that this one will be explosive and inflammable, and therefore they are used. And freon gases, these are being removed because of their environmental degradation. Will be used as among the simple gases. Air is the most important gaseous insulator because it's widely available and it provides insulation between overhead cables at practically no cost. Will be reliable as well under low voltage stresses. The average dielectric strength is about 3 to 5 kilovolts per milliliter, but will pressure. Nitrogen is used in transformers to replace air because of the content of oxygen in air. This leads to oxidizing properties, thereby oil contained within the equipment, degradation of the insulating oil, and nitrogen is then will also be used under pressure in certain types of semiconductor, such as types of capacitors, and in conjunction with oil-treated paper. Hydrogen is important because of its lightweight and good thermal conductivity, especially if you are going to be providing, when you're trying to do space equipment and the like, weight is usually a factor. It's useful as a coolant in electrical machines, such as large turbo generators, for improved efficiency. The inert gases, such as neon, argon, will be used in gas discharge tubes, such as the ones producing light for signage and the likes, and also other appliances. Oxide gases have as a pregnant for oil-filled high voltage apparatus, such as cables and transformers. So gases with high affinity for free electrons are usually referred to as electronegative. This would include the halogen gases, that is the group 7 gases, such as chlorine, fluorine, and so forth. And the electronegative gases have very high dielectric strength when compared to nitrogen or air. They are non-inflammable and also non-explosive. And the most important one being the sulfur hexafluoride, used widely in high voltage switchgear, cables, and measuring equipment, and niche applications such as gas. So it's particularly useful in power circuit breakers, X-ray and microwave equipment, and it's a colorless, odorless, and non-toxic and non-flammable gas. The non-flammability is what is most important for us because it means it's safe to use. The non-toxicity is also good because it does not degrade the environment. The others are just characteristics just to let us know what sulfur hexachloride looks like. So it has volume per volume, and it has low solubility in water. So it will be used in liquefied form by compression and has cooling characteristics that are usually better than those of nitrogen. And high thermal stability, that is, does not dissociate. Okay, it remains stable and keeps its characteristics stably over a wide temperature range, usually up to 2000 degrees C. Hydrocarbons themselves, like I said, are not useful as insulators because of their inflammability, of their high flammability and explosive nature. So when we use low pressures such as the charged particle accelerator tubes, the field emission tubes, electron microscopes, and so forth, and the dielectric loss is usually low for these systems because even the free charge or free charge carrier concentrations are very low in low gas pressures. And this breakdown of gases is usually due to radiation and ionization. So air is under this tune of 0.1 centimeter square, and when we look at atmospheric radiation, it may include one, ionization by cosmic rays, and remember cosmic rays are not as obvious that will be present in air and as well as earth, such as the radon gas. High temperature of the gas and lead to ionization when we accelerate any free charges or any free carriers in the gas to very, very high impact ionization. So very radiation of the gas and therefore stripping off the electrons from the neutral molecules. Impact ionization across the gas. So we consider ionization that occurs when a neutral molecule A absorbs a photon of sufficient photon energy h bar omega, where h bar is of course the reduced Planck's constant. And the photon ionization process of the will therefore follow the an equation of the form. That is, we have the neutral h bar omega, and it leads to an ionized gas molecule plus a free electron. In this breakdown, photon ionization will play only a secondary role, but it is essential when we have data and corona discharges that would appear around high frequency, high cable sound coming from around the wire. That is the corona discharge. So when the photon energy is insufficient to cause ionization, it will excite the electron to a higher energy level. And then we say that the molecule is at an excited level. Now, the lifetime of certain elements in these excited states will be relatively long. And this long lifetime of excited states are usually called metastable states. So atoms that have this property will be referred to as metastables, and when, okay, and because they have relatively high potential energy, they'll ionize neutral particles when they collide with them. As the electron is trying to relax back to the ground state, it will produce enough energy to ionize another material that it play with. This is used, say for example, that can be looked as follows. There is raised, we are raising it to M to show that it's a metastable, so it's in its excited state. And ionization may occur according to the process. A colliding with B leads to A, okay, the ionized A, atom A, plus the neutral atom B plus a free electron. Ionization by metastable interactions often will occur long after the initial ionization. This effect is usually used in gas discharge in argon, a mixture of argon and neon in neon breakdown gas discharge tubes to lower the ionization voltage or the dielectric strength of the mixture. So it has been shown to be responsible for the long breakdown time lags that will be observed in certain gases, leading to the effect of fluorescence and phosphorescence. Molecular collisions due to the higher kinetic energies of the molecules. The rate of new ion formation is equal to the rate of recombination under thermodynamic equilibrium conditions. And ionization is the ratio defined as the ratio of ionized to total number of particles in a given gas. Thus, if we have Ni and N being the ionized and total number density of particles, okay, in a given gas, then beta will be defined as Ni divided by N. That is the total number of the total density or particle density of the gas and the particle density pressure given as beta squared over 1 minus beta squared equal to 1 over P into that equation there where this is the Planck's constant, that is the mass of the particle, and by that. It looks like that one of Planck, okay, you can call where the energy of ionization by the thermal energy KT. So P will be the pressure. It's measured not in SI units, but in torricelli, and this height of mercury at 0 degrees or 133 pascals or newtons per meter square, okay, at 0 degrees. And EI is ionization energy of the gas, and M is the mass of the particle. So beta will depend on temperature and is therefore negligibly small at room temperature. Thermal ionization will therefore be significant only at temperatures above 1000 Kelvin. This would be found in many gas discharge tubes. Now, we look at what we call the Townsend's coefficient of ionization, and we look at the first Townsend coefficient. So we consider a low pressure gas that is filled parallel plate capacitor with a plate separation of D as shown below. So we have a gas in here, okay, and this is a capacitor. So we are using gas as a dielectric constant, and these are the parallel plates we are talking about. What happens is that because of the free electrons in here, we expect the current to increase. Then it will reach a point where all the electrons are being collected. We'll get an increase in the current again as those free electrons become so energetic as the voltage is increased, such that they lead to further ionization of the gas. And therefore, we get what we call secondary breakdown. So, in the absence of an applied field, an equilibrium will exist between the rates of electron and positive ion generation and decay through the recombination process. So the equilibrium will be disturbed when we apply an electric field across the capacitor. And Townsend then showed that the current through the capacitor will at first increase proportionally with the applied voltage, and then will saturate at a value I sat, which we call the saturation current. Increase beyond the saturation value, and this increase is exponential. And the exponential variation will be mainly due to ionization of electron-neutron atom collision. That is, the electrons are accelerated to very high kinetic energy so that when they collide with neutral atoms, they lead to ionization. As the voltage increases, the electric field between the plates will increase as well, and the electrons will be accelerated to higher kinetic energy. And Townsend's first coefficient of ionization, alpha naught, was then defined as the number of free electrons that would be created by an electron per unit length of path in the direction of the field. So suppose N naught is the number of electrons per unit volume that are leaving the cathode. In moving a distance x towards the anode, we expect that these free electrons, if they have sufficient kinetic energies to cause the nx at that position x, and will be increased through the ionizing collisions. So over an incremental distance dx, the increase in free electron concentration will therefore be given by d n of x, will be given by the alpha naught, which is the polarization, the number of free electrons per unit per electron per unit distance, multiplied by the actual number of free electrons that we have, and multiplied by the distance about which the electrons have moved. Or in other words, we can divide through by n of x, and we get that dn of x by n of x is equal to alpha naught d of x. And therefore, if alpha naught is a constant, then integrating this gives us that the actual free electron concentration at a position x from the cathode is going to be given by the number or the density of electrons leaving the cathode plate multiplied by an exponential factor, which is given by the polarization. That is the Townsend's first coefficient of ionization multiplied by the distance traveled. And therefore, at the anode, we expect that the concentration of the electrons that are reaching the anode then will be given by n of d, given by n naught multiplied by the exponent of alpha d. So, and the anode current will be collected at the anode multiplied by the anode, the density or velocity or the drift velocity of those electrons. And this gives us a value of A, the N naught, Q, Vd, multiplied by exponent of alpha naught D, and this exponential alpha naught D. So Q is the electronic charge, Vd is the electron drift velocity, and A is the cross-section area over which the anode current flows. So the exponential factor, exponent of alpha naught D, is therefore called the electron avalanche factor, and it represents the free electron concentration created by electron per unit length of path as it transits from the cathode to the anode. So the cathode is the source of the electrons for initiation, the sustenance of, and the completion of a discharge. This is because we said that for many cases in gases, photon ionization is negligible for the gases, but we can always create free electrons by shining radiation on the cathode. If you remember the photoelectric effect we were trying to discover or to discuss in physical electronics, we can always ionize the cathode material to produce the free electrons, which will be accelerated by the field between the plates and therefore lead to ionization now by the energetic electrons. So for a given material, the energy required to raise the energy of an electron at the Fermi level to the vacuum or free state is usually referred to as the material work function, and given the symbol Q multiplied by pi m, okay, in joules. material, and the surface applied in a number of ways. One, thermionic emission and elevated temperature condition. This is what is used in vacuum tubes, especially used in electronics. Okay, that is, you heat the cathode with a coil to raise its temperature, and you evaporate the electrons from its surface. Two, it can be field emission, where we apply a very high yanking the electrons from the surface through attraction by that field. Or we could bombard the cathode with energetic charged particles such as and our gas molecules, okay, will be accelerated towards the cathode by the high field applied between the plates. And when they reach the cathode, they may have sufficient kinetic energy to impart the work function to the electrons and therefore free them from the solid. Photon ionization also is due to photon absorption by the neutral gas particles as well as the cathode. So ionization processes and the cathode are then collectively termed cathode processes or secondary effects. So the current density in a thermionic emission is usually given by Richard Dushman equation, which is given by for this, and we leave it at that. We will call the physical electronic treatment that we already seen before. So suppose we let A be given by that constant. That constant we have, we provided as mk squared by that, and this usually works out to about 120 and 10 raised to 4 amps per meter square per Kelvin square, and this is usually referred to as the Richardson's constant, and therefore the exponent of that material there. Okay, and therefore Q phi m equal to Q VA, where VA is the applied plate voltage between the plates, is then the work done on an electron by the applied electric field and increasing temperature. So if a strong field is applied between the electrodes, the effective work function of the cathode will decrease and kind of thing we usually have. Say, for example, boiling water depends on the surface tension or the vacuum pressure or the vapor pressure above the water, and therefore if you covered as will increase. If you add pressure on the cover, then the water, and boiling being the release of the gases within the water. So this is the same kind of thing. That is, if we apply the pressure, say a decelerating field to the higher, so this is the kind of thing we are talking about. So if the field is positive, we'll be accelerating, decreases. So, and therefore the saturation current density will increase and will be given that we have for that material under applied electric field. This is what we call Schottky effect, okay, the lowering of the work function by an applied field. So the physical origins of the Schottky effect include the energy barrier lowering arising from the field voltage, where VA is applied voltage at the given point between the plates, and two, it's increased electron energy from the high electric field intensity between the plates. So a peak will occur in the new energy barrier that is too wide for the electron tunneling, and work function of the cathode material will then be lowered as a consequence. Hence, the current increases with the applied voltage from the saturation value, and that's what we are talking about, the secondary effects. And this effect will occur at field intensity well up to about 100 kilovolts per centimeter. And Schottky effect is more prevalent in oxide cathodes, such as thoriated or those with thorium oxide, than in metal ones, such as tungsten, because the surface of the oxide is usually more porous than the metal surface. So field emissions will be dominant at field intensity per centimeter. For impact ionization of the cathode, okay, the ion energy must be at least twice, okay, twice the cathode work function. This is because we need two electrons. One electron will be, for the free electron concentration to increase between the plates, each ion must release at least two electrons, okay? One will be used to neutralize its charge, therefore form a neutral gas molecule, and one will be the one contributing to the free. And therefore, if EK and EP are the kinetic emission energy of the molecule is greater than at least twice to the work function of the metal. So secondary process is the 1000 spark discharge mechanism. And neutral metastables that are incident on the cathode surface may also lead to secondary ionization of the cathode as well. So therefore, this leads to a second coefficient of ionization by Townsend, and we see this as follows. The anode current through the capacitor under breakdown condition will be given by Lagrange factor. That is, we take the natural logarithm of the ratio of I by I side, and we see that this is going to be given by alpha x. And therefore, when we plot the natural log of In, that is the normalized current, against the x from the distance from the cathode, at a gas pressure, we should get a straight line, as shown by the dashed signs here. But for reals, a curve that deviates from the straight line. So in the earlier investigation, Townsend had observed that the current through the parallel plate capacitor increased more rapidly than the applied voltage, as implied by the equation. And therefore, the second coefficient of ionization was introduced to account for the by positive ion bombardment and photon ionization of the gas and the cathode. And these processes lead to electron emission by one, positive ion collision or bombardment with gas molecules and the molecule and the cathode, and two, photon absorption by the gas particle as well as the cathode. So I think I have my time is up, and therefore I'll stop here. So please keep this in mind. We have reached the 1000 second coefficient of ionization, and we shall be looking at that. But over the holidays, you can be looking at this material which I've already shared on the Google Drive, so that when we resume, we can quickly go over it and finish this particular part of the electrodynamic course. So, are there any issues that you may want to raise at this particular time?
Excuse me, sir.
None, I'll take the opportunity. Yes.
I have a question. You had mentioned that nitrogen is used in transformers. Does it also oxidize to form nitrogen?
Let us ask. Yes. Nitrogen will not oxidize if there's no oxygen, isn't it?
Yes.
Are we okay?
Yes, you're okay.
Yeah, as long as we don't have oxygen there, we cannot oxidize. We cannot oxidize. So usually, like the transformer oil, also you'll have to. If you just don't get, or you can't go to the petrol station, buy oil, and then come and put it in a transformer. It has to be treated by trying to reduce the dissolved gases in it. Okay. And that's why the only people doing this are usually Kenya Power. And that's why we have oil from the transformers. Okay? Because usually you can't buy it in small amounts and you want to make your Kali welder. And only one people, the supply of that treated oil is very little. So every time to try and improve the lifetime of your insulation, there's usually a process that you gone through to try and remove the dissolved gases. So any other question? Did I answer you?
Yes, you did. Thank you.
Okay, fine. Say that I'll take this opportunity to wish you happy holidays. Try and stay safe. Don't go unduly irresponsibly partying. Try to keep distance. Okay? And let's meet next year then. And for the continuation of this, please don't try to go through the material as given, so that we can, we can start on the same page when we resume. So with that, thank you, and have a Merry Christmas and a Happy New Year.
Thank you, sir.